In classical mechanics, we assume objects move along perfectly smooth, continuous trajectories. But boundary condition quantum mechanics, or BCQM, proposes a different foundation. Here, spacetime and inertia emerge from discrete, stochastic quantum event chains. The primary variable governing this framework is the coherence horizon, denoted as WCO. This is an intrinsic timescale that controls the typical separation between interruptions in a particle's forward trajectory. At the primitive level, BCQM models a pre-spacetime foam, a featureless, rado-like mathematical graph of events and directed edges. When a trajectory reaches its coherence horizon, the path is interrupted by this ambient foam, causing sharp, jagged shifts in direction that register as massive fluctuations in acceleration. This presents a serious mechanical problem. If all motion is ultimately built from discrete, probabilistic graph hops, how do we prove that smooth, classical macroscopic inertia can actually arise from this underlying static? To answer that, we have to build a rigorously validated numerical simulation pipeline. We need a system that generates raw event data and extracts inertial noise spectra, strictly without hard-coding any Newtonian physics into the rules. The pipeline begins by defining a localized microscopic hop rule on a one-dimensional chain. The model outputs a sequence of position updates over discrete time steps, which we then convert into a time series of discrete acceleration, or AN. That discrete acceleration time series is fed into an analysis module to calculate the one-sided power spectral density. Power spectral density is a measure of a signal's power content distributed over frequency. By integrating this density over a frequency band, we extract the total noise amplitude for a given coherence horizon. We run this simulation across a grid of different coherence horizon values. This allows us to perform a log-log regression on the amplitude, extracting a specific scaling exponent called beta. This exponent translates the math into physics. A beta near zero means the inertial noise is completely independent of the coherence horizon. A beta of 2, however, represents a highly suppressed noise spectrum, matching a ballistic, classically rigid Newtonian trajectory. To prove that inertia emerges naturally, the simulation must identify a physical mechanism at the quantum level that actively drives this beta value upward, away from zero. But before we test any physical hypotheses, we have to mathematically verify that our analysis pipeline is sterile, ensuring it doesn't manufacture scaling laws out of random noise. We establish this baseline using a deliberately stationary, WCO blind control model designed to stress test the pipeline's objectivity. This control uses an Ornstein-Uhlenbeck type update rule, a mathematical model traditionally describing a Brownian particle under friction. Here, both the relaxation parameter and the overall noise scale are explicitly stripped of any dependence on the coherence horizon. Running the log-log fit for this stationary kernel yields an exact match for our expectations, an exponent statistically consistent with a beta of roughly 0. When we feed the pipeline archived toy models where artificial scaling is mathematically engineered into the steps, it correctly reads out a non-zero exponent. The system only detects beta when it is actually present. Because the control parameters are independent, any scaling we observe in subsequent experiments must originate from the actual physical microdynamics, not from an analysis artifact. This null result provides a concrete mathematical foundation. It guarantees that if we discover a non-zero beta moving forward, we are observing a genuine physical phenomenon. With the pipeline validated, we can test a physically motivated framework, the binary soft rudder kernel, which governs the motion of a single primitive quantum thread. This model enforces strict geometric constraints. The step size is fixed at an absolute value of 1, and the internal state is restricted entirely to a binary direction variable of either +1 or -1. We inject the coherence horizon into the physics by tying it to a slip probability. This dictates how often the thread loses its directional persistence and flips its internal rudder. Because the step size is rigidly fixed, every single flip in direction generates a massive spike in discrete acceleration, acting as a form of geometric shot noise. When we apply a natural slip law, where errors scale inversely with the coherence horizon, the pipeline calculates an amplitude scaling exponent of exactly beta equals 0.5. A beta of 0.5 places this single thread firmly in a diffusive universality class. Mathematically, its motion is identical to random telegraph noise, which is a type of signal that randomly jumps between two discrete values. This severely limits the model. A single thread with these local parameters cannot reach the ballistic beta of 2 required for rigid classical inertia. To force a single binary thread to achieve a beta of 2, you would have to apply a highly contrived slip probability scaling to the inverse fourth power of the coherence horizon. There is no physical justification for that rule. The code enforces a strict physical reality. Solitary, primitive quantum threads are inherently diffusive. Classical inertia cannot be a property of a single particle. If individual threads are strictly diffusive, then effective macroscopic inertia has to emerge from the collective behavior of multiple threads bound together. We test this using a cluster model that scales the simulation from one thread to an n-thread bundle, measuring the acceleration of their overall center of mass. We start with an independent baseline, assigning a coupling strength of 0. When threads do not interact, the center of mass noise is suppressed entirely by statistical averaging, scaling by 1 over the square root of n. The effective scaling exponent remains trapped near the diffusive ceiling at 0.4. To build structure, building on graph Darwinism, the model introduces a shared bias coupling denoted by lambda. This mechanism allows threads to reuse strong edges, forming coherent local patches that travel together. This chart shows center of mass inertial noise suppression across increasing bundle sizes. At a high coupling strength of 0.75, small two-thread bundles see their noise amplitude drop to roughly 60% of standard independent averaging. This graph illustrates how that shared edge coupling directly impacts the effective exponent, beta. Tight shared bias coupling actively pushes the beta exponent upward. This effectively stiffens the center of mass trajectory, forcing the group to act as a more rigid unit. While this bundle stiffening is powerful, it remains strictly bounded. For this specific class of modest local glue, the exponent peaks just below the 0.5 diffusive ceiling. We can verify the mechanical rigidity of these bundles by examining their internal flip statistics, plotted here as the effective flip coherence parameter, or kappa f. The high initial values of this parameter confirm that the measured spectral stiffening is driven by genuine synchronous interthread coherence, not an artificial mathematical constraint. Introducing even a modest shared edge coupling alters the kinematics of the system. It transforms chaotic individual paths into a unified, resistance-bearing macroscopic entity. The first stage of this simulation pipeline successfully isolates the measurement mathematics from the underlying graph dynamics, yielding an objective, testable kinematic baseline. It definitively proves that solitary particles are fundamentally diffusive, permanently locked near a beta of 0.5. This forces a physical conclusion. Classical inertia and rigidity are not axioms of nature. They are emergent, macroscopic features dependent entirely on the bundle glue of shared graph edges. However, while shared bias coupling achieves significant noise suppression, the current models still hit a diffusive ceiling, falling short of the fully ballistic Newtonian beta of 2. Simple, single-layer bundles are not enough to bridge the gap to full classical rigidity. To shatter that diffusive ceiling, future models must implement extreme glue, highly hierarchical, nested bundles that flip in near lockstep. These deeply correlated clusters will form the foundation for the next stages of the program, providing the mechanism for emergent spacetime and mass generation. By laying this computational bedrock, we have proven mathematically that if inertia exists, it must be built thread by thread from the quantum foam up.